So let's just start here. We're going to talk a little bit about acid-base properties of alcohols and phenols. And just a couple of real quick things, review-wise. Alkanes, pKa, are in the 45 to 50 range. So what does that mean about their conjugate base? If the pKa is 45, 50, what does it mean about the acid strength? And then what does that mean about the conjugate base strength? Lower acidity. So that means the conjugate base is more not as well. If the conjugate base, so this is less acidic. So that means the conjugate base is really strong. That's all I'm trying to get at, just generally. So the conjugate base for alkanes are probably the strongest bases that you can get, if you can get them, and you can. Then comes amines, and so when you have an amine, this is one that you see more often. NH2 becomes NH and then a lone pair. It actually has a lone pair on it already, so it really has two lone pairs over here. Over here is one lone pair. So this is a negative charge. All right. So, oh, great. I just drew on something you can't even see. Let me fix that. Let's do this. Yeah, so there it is. So NH2 has a lone pair, like it does here, and then you can pull a proton off of it. So again, pKa for this process is between 35 and 40, so that means that's a very weak acid. This is a really strong conjugate base again. Okay. And going on down the line, alcohols are in this sort of middle region, 14, 15, 16, 17, 18. Water's 15.7, that's a good one to remember, okay? Especially because we use it a lot when we do reactions of alcohols. And then we know that like the halogens produce like HCl, HBr, HI. Those are all strong acids. Progressively getting stronger, HI is the strongest. And then the weakest is HF, and it's actually not a strong acid, it's a weak acid. pKa's are closer to 3 or 4. Okay? Or 2, is it 2? I don't remember. I just know it's not a strong acid. The other one that is important to know in here somewhere is acetic acid or carboxylic acids. I think that's a one that you should know. Those are between 4 and 5. So how you remember, if you don't remember, we use this information to figure out like which way an equilibrium will be in the course of a reaction. So for example, I want to make a new slide. And we'll make a new slide. I can pop this one back up in a second. Let's say you have, and this is probably the most relevant. So you have a conjugate base of an alcohol, and then let's say it's a tertiary alcohol, because that's an easy one to remember. It's at the end of the range. This is tertiary. So this is going to be around 18. And then you add water to it. This is an equilibrium. This is just a Bronsted-Lowry acid base, right? So the O will pick up an H from the water, and you'll get your alcohol out like this. And then on the other side, what are you going to get? Just hydroxide, right? Because it's that proton transfer reaction. So you end up with OH minus. Okay, so pKa for water. Oh, actually, and this is for the, is for this. Just to be very clear. And then the pKa for water is about 15.7. It looks like a comma, so just pretend you're in Britain or something. All right, 15.7. And then you need to know whether or not water is a strong enough acid to protonate an alcohol. Okay? So how do you make that determination, right? If we're doing ARIO, remember we talked about ARIO a lot in the last semester. It's about stability of the conjugate base. And so if you look at these two conjugate bases, you have to say, well, is this conjugate base more stable than this conjugate base? And then you have to, like, know some things about, like, atom, resonance, induction, and orbital. Those are those things that you use to do that comparison. Or you have the pKa's, because the pKa's inherently have that information in them. So since this pKa, right, is lower than that pKa, what that means is this is a stronger acid, and so its conjugate base is more stable than the conjugate base of the alcohol. So hydroxide's more stable than an alkoxide, tertiary alkoxide ion, and so the equilibrium is favored to the right-hand side. Okay. So in this chapter, we're going to talk about later a bunch of different reactions, and a lot of times the last step is you add water. Why are you adding water? The water is just because when you form an alcohol, a lot of times this is the ion you get, and when you add water to it, you can protonate the alcohol and then isolate the alcohol that you need.
So since H2O is a stronger acid,
Yeah.
it's going to deprotonate and produce OH, right?
Since H2O, yeah. So you can think of it like this. It's like you're playing volleyball,
Yeah.
right? And water has the ball right now, and it's the better team. So when the turn is done, the ball's on the other side of the court, right? So the stronger team wins the battle. And if you don't know what volleyball is, I'm sorry. You must all know what volleyball is. The objective is to smash the ball down on the other side and get a point. Yeah. I watched a volleyball match the other day, and the rules are different from when I grew up. Now you get a point at every turn. Yeah. Used to be five serve, and if there was it used to be exchange of service, and if you won service, you didn't get a point.
Oh, yeah.
Yeah, right? And the games could go on for like hours.
You get a point every...
Yeah,
I mean,
yeah. Sorry, you and I must be older. Sorry. Yeah. I was like, what? That makes it too easy. No, it doesn't, but... All right. Make sense? So this is why we're going to go over ARIO, so we can sort of understand what makes different acids and bases stronger. Okay. Did you guys need info off this slide still? So, we're just talking about alcohols, so the atom doesn't matter because an alcohol, the H is always on an O. And orbital doesn't matter because the H is always on an O, right? It's the same kind of oxygen. Okay, so you look at cyclohexanol versus phenol, right? The only things we really have to think about are resonance and induction. Those are the two middle parts of ARIO. And phenol is, like they say, 100 million times more acidic. I just think, 10 to the 8th. But anyways, 10 to the 8th times more acidic. It's because of resonance, right? There's resonance, and what resonance allows to happen is delocalization of the electrons. And as you spread the charge throughout the structure, it becomes more stable. So in ARIO, we're always talking about stability of the conjugate base. All right. So that's the conjugate base, and then you have to show how the electrons delocalize. In this instance, I'm just going to draw one pair up here, but there's, of course, many, many pairs. It goes like that, and that. And so that's the first resonance structure, and the second resonance structure will be this one. If you don't recognize it, this is what's known as the allylic lone pair pattern that we learned in chapter a long time ago. I remember, a long time ago. I think it's 3, but I'm not positive. There'll be another one that goes like this. Oops, did the wrong carbon. And then one more. I'm pretty sure I talked about this, but that's okay. It's worth doing again. Like that. And then one more, but it's not really one more because it kind of gets you back to the original molecule, except for the bonds in the benzene ring have rotated around. And you don't have to draw all of those. And so that essentially takes you back to this original structure. Except for the bonds in the benzene ring are now, every, like, here and here instead of where they are. So relevant resonance structures, there's at least 4. If you count all the other ones, and there's like a whole bunch more, but there's a lot of resonance structures. One of the things I mentioned in talking about, this is it almost sounds like an inductive effect. I'm pretty sure I mentioned this the other day. If you put an electron withdrawing group here, like a nitro group, and then you have this at this resonance structure. So what I've done is I've taken this resonance structure and added a nitro group to it, okay? So this would be like nitrophenol. It would be known as 2-nitrophenol. Then what happens is this pair of electrons can delocalize now into the nitrogen and spread the charge out even further. And as a result, putting nitro groups on like a benzene ring causes whatever substituents are on there to be more acidic, provided they're in the right position, because for resonance, it definitely matters where this nitrogen is, because if it's here, right, there's never a lone pair at this position in the structure. And so it can't delocalize those electrons to the nitrogen. The lone pairs are only ever in the 2 and the 4 positions. Or if you want to say 5, 2, 4, and 5, but 2 is like the reverse of 5. So they're only in the 2. We usually think of it as the 2 and the 4 positions. Okay, so this pair of electrons then can delocalize in the nitrogen. So pKa's of things with groups like nitro groups tend to be lower, that is stronger acids than things without. And if you put 2 nitro groups on, guess what happens? It gets stronger. Right? Now, in general, these kinds of groups are known as electron withdrawing groups. I'm just going to abbreviate it. EWG. Because they pull electron density out of the ring. And so if you have a negative charge that develops in the ring, putting electron withdrawing groups on the ring causes it to be more stable. Okay? And you'll see this is actually an important part of mechanisms that we learn in later chapters, the addition of electron withdrawing groups on the ring. Questions? You're such a peaceful class. So chill, I like it. Man, that other class? Sorry. We have members of that other class in here, but they're not as loud today.
You get a lot of questions or what?
I just get a lot of talking. No, a lot of questions too. There's a lot of stuff being asked, but it's just really loud. I think it scares like new students away. It's like they come in, they're like, "Oh man, these guys are crazy." Okay, so I already kind of went over this, but here's the question, right? Will sodium hydroxide be strong enough a base to deprotonate phenol? And so then to ask the question and get the answer, you should write the reaction out, okay? Eventually, like, you'll get to the point where you go, oh yeah, of course it is, right? But at some point, you have to learn how to think about it. So you just literally write down what it says. Here's phenol. Oops, and sodium hydroxide. You can do NaOH, or you can just do OH. So you could do that, or you could get rid of that and just use the OH minus, which is what most of us, I think, are used to seeing from Chem 1B, so I think it's okay. This is going to be an equilibrium. And then you apply the Bronsted-Lowry acid-base theory. It's just a proton transfer. So the product of this will be this ion, which is known as the phenoxide ion. And water. So then you just have to think about pKa, or look at stabilities, and you look at this and say, oh, this has resonance stabilization. That one doesn't. Definitely it'll go this way. Okay. Or you could say, oh, pKa 10 versus pKa 15.7. So which is the stronger team? Team phenoxide. Sorry, I don't want to make that sound like a slogan. But yeah, so definitely the phenoxide's the stronger team. The ball's going to end up on the other side. Yeah, that's a pretty good analogy. I like that one. Sorry.
So higher pKa is more acidic.
Higher pKa is less acidic. Lower pKa, stronger acid. Yeah. So that's resonance, and then there's induction. Oh yeah, I know where we got to. This is good that we reviewed this because it was at the very end of the last lecture. We got rid of A, we got rid of O, so we did R, so this is I. This is induction, okay? And inductive effects, right, or we call them through bond effects, and trichloroethanol is a stronger acid because there's a partial positive charge here, because these are partial negative. The electronegativity difference is what causes that. So you got this big electronegativity difference, or you got an electronegative difference. You got three of these groups on there. That puts a positive charge at the carbon where they're attached. And one of the things to remember is if you can put a positive charge near a negative charge, it helps to stabilize it. And so,
That's the induction effect, right?
yeah, inductive effect, yeah. So when the ion for this forms, that partial positive charge helps to stabilize the negative charge that's on the oxygen. And then whatever the conjugate acid is of the base that did that, it'll be over on the right. So something like this, actually, because the pK is 12.2, and something like water, right, whose pK is 15.7, tells you that if you wanted to make this ion, you could use sodium hydroxide to do that. Right? If you wanted to deprotonate ethanol, you can't do that. Because pKa is higher than the pKa, or too close to the pKa of hydroxide or water. And as a result, you can't use sodium hydroxide to deprotonate ethanol, but for trichloroethanol, it should work pretty well. Now, there's another thing, I remember talking about this now because it's the thing that I learned wrong years and years and years ago. Is solvation effects. And I really blew through this, but here are the pKa trends for T-butanol and ethanol, and which one is stronger? Ethanol, right? and weaker is T-butanol. And it used to be, the way the thinking was, this is wrong, I'm just going to tell you, this is wrong. We treat methyl groups as electron donating groups. And all the other stuff we do, right? And that's through hyperconjugation, right? And so one of the thoughts used to be is that these are electron donating groups, so they put a negative charge over here, right? So that when you pull the hydrogen off, there's a negative charge over here, and that makes it less stable. And as a result, the less stable conjugate base, right? Weaker acid. Right? This one has a more stable conjugate base because there's no negative charge being donated to that carbon. So that's the way we think all the time, and it turns out it's wrong. And the reason it's wrong is because the reason we know it's wrong is because when you look at this same trend in the gas phase, okay, T-butanol is stronger. And the only thing that's changed is whether it's in the liquid phase or in the gas phase. And if it's an inductive effect, all the through bond effects should be the same. So we know it's not an inductive effect because we're not changing the structure of the molecule. We're just changing its surrounding. And so what they know the difference is, I suppose I should have learned this because it was like in 1968 or something they figured this out. So it was like I was well into my school years. By that time, 68, I was 4. So, I mean, I wouldn't have learned it at 4, but by the time I got to college, somebody should have told me, right? Anyways, nobody told me. Or maybe they told me, and I do like a lot of students normally do. Yeah, that's really interesting. Great. It's probably in a warm room just like this one. Oh, man, I got stories about warm rooms. But anyways, so it's a solvent effect. Because the difference between the gas phase, right, and the liquid phase are how close the molecules are together. And it's the proximity of the other molecules that causes T-butanol, or ethanol actually, to be more stable than T-butanol. Okay. So you can think of it like this, right? Here's T-butoxide. Remember we talked about steric hindrance. Steric hindrance prevents SN2 reactions and those kinds of things. But it also prevents ions from stabilizing the charges down on this part of the molecule. And the bulkiness out here, like the big shoulders, helps to prevent the stabilizing effect of solvent on this side. Now what's the solvent? Well, it could be water or it could just be T-butoxide. Right? But because this part is so bulky, you can't stabilize the charge, the positive charge that develops here. And because this thing is so bulky around here, you get less solvation, as we call it, from the solvent shell on this side. And as a result, ethoxide ions are more stable when they're in solution than butoxide ions, or T-butoxide ions. Yeah, pretty simple, sort of. So now we have ARIO that we have to deal with in acid-base strength, and we have to think about solvation effects. So we need to figure out this kind of questions you get. Use ARIO and solvation to rank the following molecules in order of increasing pK. So the way I like to do these problems is divide and conquer. Right? I look for molecules that look the same, and I try to make comparisons. And things that pop out to me, for example, are like, oh, look, there's pi bonds on the top one. That may have resonance effects. I'll do those separately than the bottom ones because they don't have any pi bonds. And so it kind of simplifies the things that I have to think about. So I draw a line here just mentally. And then I'll deal with the bottom one first because there's less things to think about. So here, you have bulkiness, right? You have these ethyl groups, and here you don't have any. So what does the bulkiness tend to do? It reduces the ability for solvation effects, so that's going to be the weaker acid. So I'm going to go weak on this side and stronger on that side. I'm going to do the same comparison at the top, and then I'm going to try to find a way to bridge the two in the middle. Like, how do I link all this stuff together? Okay, so they're all alcohols. So I really only need to think about resonance and induction. Resonance is a more important factor than induction. That's why in the ARIO scheme, it's first. Right? So atom, resonance, inductive, oxygen. Otherwise, it would be ARO. Ever think of that? Huh? Like, there's a show called ARIO? Huh. Is this something that I would enjoy? Maybe?
It's about superheroes.
Huh?
It's about superheroes.
Green Arrow. It's DC Comics.
Oh, I love Green Arrow. Yeah. Oh, we should just make it green then, but then everybody would get confused. Sorry. Arrow, I get it. Huh. I'm like, there's actually an AIRO? What? All right, what about these two, right? Got double bond here, got double bond there. Which one's stronger, left or right? Right? Why? It has resonance. And you have to remember, right, in order to have resonance, it has to be continuously conjugated, which means sp2 all the way across. There's a hydrogen here. This is sp3. So the pair of electrons that would develop on that oxygen aren't able to delocalize to the other oxygen. On the other hand, this pair, that's that allylic lone pair pattern again, can do that. Okay? So because it can delocalize charge and put it onto that nitrogen, it's going to be a much stronger acid. So here I have stronger on the right, and on the left I have weaker. So kind of to bridge all this together, right? Compare these two, because they're the most similar of the bunch. This is going to be stronger than that one. But now to know whether or not the top two go first or the bottom two go first, right? You just have to look at these two. And it's not significant necessarily, but which one of those is probably the stronger acid? The one on the top, right? So if I number these, 1, 2, 3, actually let me do this. A, B, C, and lowercase b, sorry, D. All right. Strongest then is B, right? So increasing pKa means you want the weakest one at the right and the strongest one at the left. So B is the strongest, so I'll start with that one. Then A is stronger than C, right? So then it'll be A. Oh, I just want increasing pKa, so I'm going to go like this. And then C. And then D is the weakest, so it will have the highest pKa. My one warning is, right, on your final, it's multiple choice. That order is there, the reverse order is there, the greater than equals are there, right? You have to get it in exactly the right order. On many occasions, students just do what they're thinking, and they'll do something like this. And I'm like, it's exactly backwards. What are they thinking? And sometimes you'll see this, oh, strongest acid. And you're like, okay, I know what they're thinking. And on a written test, I give full credit because I know what they're thinking. On a multiple choice test, it's wrong. Right? So think about how you answer these questions. Okay. Okay, so this whole next section is how you make acids and what kind of reactions acids undergo. So we call the how you make acids part preparation of acids. And we learned in chapter 7 that one of the very common ways to make, oh, it said acids, alcohols, sorry. very common ways to make alcohols is to do substitution reactions of alkyl halides. So you can have SN1 or SN2 mechanism. SN1 is that, right, stepwise form the carbocation, nucleophile comes in. And SN2 is the concerted, you might have to modify something sometimes, but then nucleophile comes in. Then when you're doing an alcohol, you're usually deprotonating or using sodium hydroxide, and then you don't have to deprotonate. So there's actually two different mechanisms, both end up in alcohols. So examples are for primary alkyl halides, and the halide could be usually, it could be chlorine, bromine, or iodine. Usually not fluorine because the bond's too strong and it's a bad leaving group. We prefer, if we can, to use a better leaving group, but you know, chloride as a leaving group is not a horrible leaving group. But bromide is definitely a lot better, but that's not what we have on the slide, so there you go. So this is an SN2 mechanism. We know it's SN2 because it's primary, right? And primary can only undergo SN2 because the carbocation mechanism is too unstable. The carbocation doesn't have enough stabilization. On tertiary, you can do, I can smell it. Cyclopentadiene is slowly wafting into the room. Sorry. It's really strong smelling. When you get a real good whiff of it, you're like, oh, can I go out and throw up now? Some people do. Some people are like, oh, I love that smell. I'm like, okay. Each his own. The other mechanism that's very common is to do an SN1. SN1 is typically used at tertiary alkyl halides because it's steric hindered, carbocation stable, but we usually do this for alcohols at tertiaries because there's no rearrangement from a tertiary. Tertiary is the most stable generally. And so primaries are always SN1. Because it's SN1, you can use a strong base. You can use sodium hydroxide, which is a strong base. And even though it could cause elimination, substitution is much faster at a primary than a secondary tertiary. Here, you couldn't use sodium hydroxide because it would just cause elimination. And you would get an alkene out of this instead. So you have to use a weak base. It's also a weak nucleophile. And that favors the SN1 mechanism. It's also protic.
Strong base, or strong, very strong base always favors elimination.
Yeah, except at primaries.
Except that primary?
Yeah, the only time strong base doesn't favor elimination is at primary because substitution is much faster there. But otherwise, strong base everywhere else, elimination is the product. Yeah. Yeah, good to just remember that good general thing because it helps you a lot. Okay, so if it's secondary, we have a couple of different strategies, and this isn't even all of them, but there's a couple of different strategies to form an alcohol directly from an alkene, okay, or from an alkyl halide. If you have an alkyl halide, the first thing you do is you make an alkene if you want it to be secondary, perhaps, and then you can do dilutes H2SO4. This is bad because it's a carbocation mechanism, right? Form a carbocation, you can get rearrangement. Sorry, my hand's too close to the screen. The other thing that you can do is you can do oxymercuration, demercuration, and this forms a secondary alcohol from a terminal alkene. And it does it without any rearrangement because it doesn't go through that carbocation mechanism. It forms that cyclic mercurium ion. Tablet stopped working. Still recording, I think. Yep, still recording. Okay, so, and then if you want to make a primary alcohol, the principal way that we have is to use hydroboration followed by oxidation. Hydrogen peroxide and sodium hydroxide. These two don't suffer. The bottom two don't suffer from rearrangement. You don't get carbon. Any questions? Yeah, go ahead.
I don't know if this was basically for the acid catalyzation and
Oxymercuration? Yeah.
Is there any, not priority, but is there any
Just
situation
depends on
where-
if you have to worry about rearrangement.
Okay.
If there's not rearrangement, then no, but you're still gonna get other products. There's still hydride shifts that go on occasionally.
Okay.
So if you're gonna do a secondary, maybe oxymercuration's better. If you're gonna do dihydroxylation, that's the other thing that we learned about in 28A. We usually use things like osmium tetroxide, permanganate cold. There's the whole epoxide followed by sodium hydroxide, epoxidation reactions. And, I don't remember if I have slides on that, but if I don't, I'll go over those later. Just remind me. I seem to have disconnected, but I'm still recording. I don't actually have any control over my computer right now. Oh, well, I'll just change slides. Oh, so before I talk about oxidation reactions, these are and reduction reactions are like how you can make. This is not working. I'm just going to set it to the side until it says he's back. It's really a bummer. It's been working pretty good this semester, and all of a sudden it just went wigged out. We need to talk a little bit about oxidation states. Okay, so you remember how in Chem 1A you had this whole, like, how many valence electrons, you know, all this stuff. You figure out the oxidations, not valence electrons, but you figure out whether it's more electronegative, less electronegative. You try to say oxygen's -2 and hydrogen's +1. And so I'm going to teach you like a really easy way to do it. Okay. And a really easy way to do it is this. It's simply to say, well, in formal charge, we think about sharing of electrons. In oxidation states, we just think of the bonds breaking heterolytically, and every time it breaks, the electrons go to the side that's more electronegative, right? And then you just add up the pluses and minuses. So for example, here, this is for methanol. You want to know the oxidation state of this carbon. Well, carbon, just remember this, carbon's more electronegative than hydrogen. Everything else is kind of obvious, but carbon's more electronegative than hydrogen. So when it's bonded to hydrogen, this is a -1. That's a -1. And that's a -1 because you're all hydrogen. But when it's bonded to an oxygen, it gets a +1 because oxygen's more electronegative. It's double bonded, it would get a +2 because it's 2 pairs of electrons in its state. So let's see if we can do this. Plus, minus, minus, minus comes out to -2. So the oxidation state's -2. I like that way. It's so easy. So we're going to do all of these, okay? Reconnect. I think my network dropped out. My iPad switched to a different network. Okay, so here's methane. I'm going to plug something back here just a second. Figure out what the oxidation state is. Right? What do you get for this? -4. Because hydrogen's going to be losing the electrons, carbon's more electronegative. So -1, -1, -1, -1, it's -4. Here we already did this one. This is -2. And this one, -1, -1, +1, +1, 0. Okay? And this oxidation state is +1, +1, +1, -1, so +2. Okay. And what's this one? +4. Okay. Oh, it came back. Good. So let me write all those down real quick. So this is -4. This is -2. This is 0. This is +2, and this is +4. Okay, so we're talking about oxidation reduction. Oxidation, if something's being oxidized, that means the oxidation number's going up, Oh, seems to have lost contact again. I have a lot of writing on my screen. It's not on your screen. Can you even change slides? Bummer. Okay, this is what I'm going to do. I'm going to pause the recording. Okay, so yeah, it's really wigging out on me. Not working now. Okay, so you guys have the numbers for these. Oxidation is when you go from lower oxidation to higher oxidation. So the direction of oxidation starts on the left side and goes all the way to the right. That's the most oxidized state. And if you want to do that, right, if you want to oxidize, let's say you want to take methanol and make carbon dioxide out of it, you have to use a strong oxidizing agent, right? And if you think about how these reactions are going, typically you need for these reactions an oxidizing agent or a reducing agent, and they all classify. If you know chromates are oxidizing agents, permanganates are oxidizing agents. It's peroxide is oxidizing agent. You can use those lots of times. Like if you don't know, you can use those, and a lot of times the reagents are interchangeable. If you want to go from like formaldehyde to methanol, then you need, because this is going the opposite of oxidation, you're going to need a reducing agent. So one of the things I did many years ago, I made a list of all the oxidizing reagents and all the reducing agents, put one on one side of the page and one on the other side. So I'll give you guys that to help you with your synthesis problems. It includes things for the whole year, like both semesters. Okay. So oxidation or reduction. Oxidation, say on the left, is reduction. Yes. It's 0 there, and it's, what's it here? So this is a little tricky because so this is, see if this will work again. It keeps popping in and out on me, and it's really hard to stop writing on the screen. So this is a carbon out here, right? Oh, it's working. So plus or minus here is actually just 0 because it's bonded to a carbon. So this one's +2 because it's bonded twice to oxygen. So if you think about this is 0, 0, and this is 2 plus up here, then the whole thing is +2. Here you have to not forget there's a hydrogen here. Okay? So that is 0, 0. And then carbon, this is -1 for this one, and it's +1 for that one. So this one's 0. So this is a reduction. This one is overall +2, and the one on the right is overall 0, so this is reduction reaction, and so you need some sort of reducing agent. So what do you need to have in order to have a reducing agent in this reaction? What's the element that you have to have for a reducing agent? It's to be part of it. Hydrogen, right? And one of the things that you learn in biology, and one of the things you learn in chemistry, when you do biochemistry, is most biological reduction reactions involve proton transfer. They're actually transferring hydride ions, H plus and a pair of electrons. Okay? So NADH and NAD plus, right? What is, if you're going, little side note, you're going NADH, and this is a big giant molecule, right? And you're making NAD plus. What's the part that's missing? H, right? Minus. So H minus is hydride. So NADH is a reducing agent that does hydrogen transfer and electron transfer. And if you wanted to reduce this, it's very possible that NADH could do this reduction reaction because it has the necessary components of electrons and hydrogens. And then if you notice there's only one hydrogen here, it may be the other hydrogen comes from the solvent, right? And so all that's necessary is the solvent is able to do a proton transfer to the oxygen at the end. Okay? I'll show you how the mechanism works. The other real common reducing agent that we see in class all the time is just metal catalysts, right? But it has the necessary components, H2, and then you have platinum, palladium, or nickel. They say forceful conditions, high temperature, high pressure. That's kind of true. It's not always necessary. You guys did hydrogen reduction of an alkene, right? And you used H2 and palladium, and I know our yields weren't great, but some people got good yields, right? Was that high pressure or high temperature? No. You were bubbling it in a glass flask, and it fully reduced the alkene to an alkane. So yeah, you don't always, like, they're trying to make a point here, and I don't think that's necessary. Now, if it's benzene, if you want to reduce benzene, benzene's really stable, then it is really high pressure, really high temperature to reduce that. Okay, so here's the problem with this reaction. Not very discriminating. If it sees any pi bonds, it reduces all of them, okay, except for maybe benzene, because benzene is so much more stable. So, I'll give you an example. Let's say you had, I'm going to try this again, but if it doesn't work, I'm going to be really pissed. Let's say you had this reaction. Makeup reaction time. Look at that. I think the same one I used yesterday or something similar to it. Like that. Okay? And you did H2 and a catalyst, like, let's just say palladium, because that's what we used. What you would get is that. Because the hydrogen is not very discriminating. If it's a pi bond, it's a pi bond, and you can put hydrogens on it. That's all it thinks of. So interestingly, there's a whole set of metal hydride reductions. Sodium borohydride, for example, which is part of the lab. If you do sodium borohydride, you know, I'm going to stick the other hydrogen on there. I just wanted to show there's the hydrogens from the reduction. That's what you get. So inherently, there's something different about like a ketone and an aldehyde than an alkene. And if you have an alkene and you don't want to reduce it, right, you can selectively reduce an aldehyde, a ketone, a carboxylic acid, an amide, a nitrite. There's a bunch of stuff you could selectively reduce, okay, using sodium borohydride or lithium aluminum hydride. So what's the difference in these pi bonds? There's the pi bond on this side, and there's the pi bond on that side.
One has oxygen.
Yeah, and what does the oxygen do to that bond? Huh? It weakens it? Not necessarily, because the oxygen's smaller, so the bond's actually pretty strong. Drawing electron density, because it's more electronegative. So CC double bonds, right, just alkenes, nonpolar. aldehydes, ketones, carboxylic acids, amides, esters, blah, 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 blah. Okay? Polar. The polarity is caused by the presence of an oxygen instead of a carbon. So here's the thing. Why does that matter? Right? It's more reactive to sodium borohydride. Well, what is sodium borohydride doing, right? Or NADH, same kind of reagent. What is the sodium borohydride doing? It's got to transfer a hydrogen, right, and electrons. What's the charge of an electron? Negative, right? And so when you have reagents like borohydride, they naturally try to transfer first to a positive charge. And the oxygen provides the positive charge of the carbon. So this is positively charged. And so when you're transferring H minus, hydride ion, that's where it attacks. It attacks at that charge. And that's why it doesn't attack the alkene, because the alkene doesn't have any polarity associated with it. So the mechanism for the sodium borohydride reduction looks something like this. Okay. Ethanol, methanol, water, any of these things can be used. Just be wary that when you do this reaction, like at the end of the reaction that we did on, or maybe you're doing today, we heated it, right? That actually causes a different reaction, but that causes the evolution of hydrogen gas. We'll talk about that in a second. But in this main reaction, your principal goal is to reduce a ketone or an aldehyde to an alcohol. Okay? Now, if it's an aldehyde, you get a primary alcohol. If it's a ketone, you get a secondary alcohol. So remember what I was just talking about? The charge at the carbonyl carbon is partially positive. So borohydride can be written like it's shown down here, with a boron and a negative charge on it, but it's not happy with that negative charge, so it transfers the pair of electrons to this positive center. When it does that, the carbon has to release one of the bonds it already has, because it's going to violate the octet rule, and kicks that pair of electrons back to the oxygen, and this is your intermediate. And then you need a solvent to protonate it. Okay? And since like secondary alcohols and tertiary alcohols produce stronger conjugate bases than water does, then you can protonate that with the solvent. Okay? Also, in general, this is the solvent. There's just a lot of it. So just using Le Chatelier's principle, force the equilibrium to the right. Pretty straightforward mechanism, right? Understanding that that's the positive center. Hydride is being transferred as a hydrogen and a pair of electrons. That's where the arrow goes this way. And then the oxygen just needs to be protonated. And usually it's water or the solvent or whatever is the proton source. Okay. Now, why do I have two of these slides? Oh, just an example of lithium aluminum hydride. You can also use lithium aluminum hydride. Okay, so lithium aluminum hydride is the same as sodium borohydride. It's a lithium ion, and then you know how you learned in Chem 1A when you drew Lewis structures of ions, you put brackets around them. This has aluminum. Looks like this. Sodium borohydride would have a sodium on the outside and a boron on the inside, but that's the only difference. Lithium aluminum hydride, you cannot use it with an alcohol. It will blow up in your face. I mean, you could, and have it blow up in your face, I guess. That's the way to put it. But it's very reactive. Lithium aluminum hydride, like if you can do it with sodium borohydride, the governing principle is you should not use lithium aluminum hydride. Sodium borohydride is a much gentler reagent. So what's the question? Why is that, right? Why is lithium aluminum hydride so much more reactive? If you think about the way these reagents work, okay, boron, hydrogen is more, let's see how I say this. Hydrogen is more electronegative than boron or aluminum, okay? That's why it carries the negative charge with it, because hydrogen's more electronegative. And that's what allows it to do a hydride transfer. Well, aluminum is less electronegative than borons, so the negative charge resides more strongly on the hydrogen, and so it's more reactive. It just has to do with electronegativity difference. So this bond here, in the corresponding borohydride, these bonds here are more polarized. The hydrogen is more electronegative than aluminum, and you can just get that from the trend in the periodic table, like starting from the top to the bottom, lower electronegativity at the bottom. So same exact mechanism though. There's the aluminum hydride, transfers the negative charge to the partially positively charged carbonyl carbon, right? And then in a second step, right? So this is the first step of the reaction. Notice the 1,2 here. Right? You run this in something like ether, which is an aprotic solvent. So you can't use protic solvents with this. Just do it in something like an aprotic solvent. And then the second step is you add water. Now, you have to be really careful when you add the water. Right? Typically what they do is they get it as cold as they can get it without it completely freezing out. And they add drops of water to it, right? And then they let it warm up to room temperature and they stir it. Because it liberates so much heat and so much hydrogen gas that it could ignite and then go off. In sodium borohydride, right, much less reactive. So the solvent that you use is actually a protic solvent. Now, if you remember yesterday, or 2 days ago when you did the experiment, right, and you had the sodium borohydride, it was bubbling all the time. The bubble was actually the sodium borohydride reacting with the solvent and producing hydrogen gas. The reaction looks like this, if you write it out. Did you have methanol? What did you have? You had methanol, huh? So let's just use methanol. I was going to do ethanol because I always do ethanol. I mean, you know what I mean. I'm always doing ethanol 24 hours a day. Woohoo! Sorry. Oh, my oxygen's screaming. What it looks like? Maybe he's singing. This is a partial positive. Borohydride looks like this. Got the negative charge here. Just does that. So that's what those bubbles you're seeing in your solution are. But in principle, the aldehyde, the ketone that you had, should have reacted already, actually. Should have gone faster. And then the heating is just to get rid of the excess sodium borohydride. So you get BH3 like this. And then the other part of that is H2 gas. Okay. And then you'll end up with a methoxide ion also. I didn't write that on there. Maybe I should. Methoxide. That's the other part of it. Okay. Well, that reaction, if that's aluminum, is just so much more violent that that's why you can't do this. You have to use in lithium aluminum hydride an aprotic solvent, something without hydrogen that can transfer. Let's see. So just comparing, right? The yields are very good, right? And sodium borohydride, you just include the proton transfer source at the end as the solvent, lithium aluminum hydride has to be done as 2 steps just because it's so much more dangerous. My son does these reactions, and I'm like, ooh, that's cool. They do it with like liquid nitrogen. And, I mean, they get it really cold and run it really slow. And then they warm it up. So just a couple of, just sort of a comparative slide. Carbonyl, alkene, right? Sodium borohydride, lithium aluminum hydride, same product. Not reducing the alkene. If you did H2, right, and a metal catalyst, you would end up reducing both. What if you wanted to do, oh gosh, it's a 7-membered ring, of course, the one I hate to draw. What if you wanted to do that? You can't go directly, but you can go like this. You can take this product and oxidize it. And you guys learned one of the reactions in lab, PCC, PPC. And you can oxidize it and get to that product. So you would first do like the complete reduction and then reoxidize the alcohol. Let's see. There's also derivatives of hydrides that you should be aware of, where you can modify the reactivity of the hydride that's on the structure simply by you buy these things, right? With substituents, the R groups, things other than hydrogen, so they could be alkyl groups, they could be electron donating groups, they could be electron withdrawing groups, they could be all kinds of things that you can have modifications for. But basically, they all do the same thing. So if you see aluminum with a hydrogen on it, it's a reducing agent. Think NADH. Most of you don't know the NAD. You just know it's got H on it, right? The same thing here. All that other stuff, it doesn't matter. It's still a hydride transfer agent. Okay. The other thing, though, that lithium aluminum hydride does, and this is not something that sodium borohydride does as well, although commercially, this bottom process is one of the big commercial processes. And they use sodium borohydride because even though the reaction's not very good, it's a lot safer than sodium borohydride. So they just use huge excesses of sodium borohydride and just run the reaction. Okay. But here, right, lithium aluminum hydride can be used to take a carboxylic acid. Oxidation state is +3. Right, and convert it to an alcohol, and this oxidation state is +1, I believe. Yeah, -1. So you can use lithium aluminum hydride to do that. You can use lithium aluminum hydride to reduce an ester to primary alcohol. The mechanism is interesting. When you do lithium aluminum hydride and a carboxylic acid or an ester. The ester one is much easier to see. The aluminum transfers the hydrogen to the carbon, just like it did in the first one. But under these conditions, right, this methoxy group that's here, that's called a methoxy group because methyl connected by oxygen, is actually a good enough leaving group that the tetrahedral geometry of this puts in enough strain that when this comes in and pushes out the methoxy group, it's a favorable process, okay? So what happens if you do this? What's the outcome of doing something like that? Get a double bond, right? That plus MEO minus. Again, we'll cover more of this stuff in the next chapter, actually. The nomenclature. That's methoxide. And guess what sodium borohydride or lithium aluminum hydride does to this? Transfers another hydrogen. So you use 2 moles of lithium aluminum hydride, and then you can reduce this. Okay? So the next part looks like this. There's the thing I just drew. Second equivalent of aluminum hydride transfers a proton to this carbon, right? And this picks up in the subsequent, when you add the water part, picks up a proton and becomes an alcohol. Again, it's the same mechanism, just it happens twice. Hydride transfer, loss of a leaving group, hydride transfer, protonation. Okay. Cool. It asks which steps in the mechanism are reversible. All right. This first one is not. For it to be reversible, they mean the hydrogen will leave. But hydrogens are really like strongly basic. Like hydrides are very reactive, so it's not going to leave. So that one's not reversible. So that one's not reversible. The only one that's really reversible is this last step. So it just really just goes in this one direction. Okay, so let's say you did sodium borohydride with this compound. Well, this will be where we end. What do you expect to happen? Yeah, proton transfer. The only part that the sodium borohydride can touch is the aldehyde and the ketone, and not the ester. This is a cyclic ester. So it can't touch this, but this is the part that it can reduce. Neither one of them will reduce that.
You said that the sodium, the sodium borohydride,
Hydride, yeah?
it's more attracted to the polar
Yeah.
side.
So this one's polar, right? And this one's polar. But it turns out because the oxygen can donate electrons to this carbon here, it's not polar enough for the sodium borohydride to react with it. Okay? So this pair of electrons can donate over to this carbon. As a result, that's why we have to use lithium aluminum hydride. Lithium aluminum hydride is even more negatively charged, and so it attacks that center. Okay, so sodium borohydride would attack this center and not this center. Neither one of these reagents attacks just an alkene because they're not polar. Okay. So the result is the product of this reaction will look something like is it the 7-membered ring again? Good God. It's so hard to draw it right. Will look like that. Okay? And then for lithium aluminum hydride, that's actually the really tricky one. What happens with lithium aluminum hydride is that this will get reduced. This will get reduced as well. Okay? But go back a second. Or do you need to still copy more on that last slide? It kind of zipped on. I can leave it like that. Okay. The lithium aluminum hydride is going to attach here, put a hydrogen here, and then this is the leaving group. But the leaving group is attached to the molecule. So it's going to be attached still. Okay. So just draw this really quickly. I'm going to sketch it out again, but not with all the other stuff on it, just so you see how it works. Draw a cyclic ester, like this. So lithium aluminum hydride, I'm just going to draw this as lithium aluminum hydride then instead of drawing the whole thing, so it's a little bit cleaner to look at, right? This hydrogen is going to attack where? The carbon of the carbonyl. And that'll cause this to open up like this. So the intermediate structure will look something like this. Now, the lone pair of the electrons will do this, and then this group leaves. Okay?
So it's gonna open it up.
It opens the ring up, yeah. And so you'll end up with that bond being broken, right? And then what happens? If it's lithium aluminum hydride, a second one comes in. So this represents my LAH, okay? It'll attack here, and that will become an alcohol as well. Let's keep doing that. So you end up with that. I didn't draw the hydrogens that attached, but there's two hydrogens there. Bond, it's opened up, and then that's step one of the reaction. That's what's going on. Step two is to add water. Like I said, to get it really cold, add the water. And that's what you end up with, okay? So that's the same process you go through for that previous slide. You just take the ester and you put two alcohol functional groups there. That's the transformation. This is the mechanism.